Alright, so in this video we go over section 6.1 composite function. So in this section we're going to find composite function and find the domain of composite function. So what is a composite function? Well, typically when we were working with regular functions, for example, f of x equals x squared. So we evaluate the function at the number 2, for example. So all we do is plug in the number wherever you see the letter x. Now in composition function or composite functions, we are going to evaluate a given function, but what we're going to give the function to it, it's not just a number but another function. So first of all, let me give you a picture here of what it means, the formal definition, and then a short picture. Well, given the functions f and let's call it a g, the composite function denoted f circle g, which we read f composed with g, or sometimes we call this f bubble g. There are two ways to read this, and it's defined as follows. So f circle g, so we have the function f and we substitute another function g. Actually, notice how this goes in order. The first function that we write is the one that goes outside. All right, so the domain of this composite function will be all numbers in x in the domain of g, such that g is in the domain of f. Well, we're going to look at this more in detail when we move on to the examples. First of all, let's look at an example here. So for example, let's say I have as an input x equals 3, for example. Okay, and this machine right here is going to perform the function f of x equals something simple, x plus 4. All right, so if we input the number x equals 3, we're going to do f of 3 equals 3 plus 4, which will be the output f of x equals 7. All right, now this output is going to go through a second machine. So now this input, the output from the first function will become the input of a second function. Let me call this g of x, and let me make something up. How about 2x minus 3, for example? So all we do again, plug in 7, 2 times 7 minus 3, that is 14 minus 3, and g of x will be 11. Okay, which in fact, if we're strict with the notation, what we're really doing is f of g of 3, and that's what we get, 11. So let's do a few examples. So suppose we have the function f of x equals 2x squared minus 3 and g of x equals 4x plus 1. Find each of the following. So first, we are going to find the composition function or the composite function of f evaluated at g. So let's change the notation. So we are going to work with the function f, which is 2x. I'm going to open parentheses, 2x squared minus 3. But what are we going to replace in the place of x? So in this case, we are going to place the function g, which in this case is 4x plus 1. That is g. Okay. And let's simplify this to lowest terms. Of course, let's expand the binomials. That is 2 times here. This is 16x squared plus 8x plus 1. So we expand the binomial, subtract 3, and then the next thing we do is distribute the 2 about every single term. So we're going to get 32x squared plus 16x plus 2 and then minus 3. So our final answer, all we need is to combine these two numbers, which in this case is 32x squared plus 16x minus 1. Final answer. Okay, this is a 1, not a 4. Okay, that's a 1. Now let's do the composition the other way around. So in this case, we are going to start with g, and we are going to plug in, we're going to substitute the function f to it. Okay, so the function g, which is 4x plus 1, I'm going to have 4 times x plus 1, but in the place of x, we are going to substitute the function f, which in this case is 2x squared minus 3. Let's highlight this just so you can see where are these coming from. Alright, and then let's just simplify this by distributing the 4. So that's going to be 8x squared minus 12 plus 1, and negative 12 plus 1, that's going to give us 8x squared minus 11. Alright, there's something here very important to notice when it comes to the order of the composition. In general, f bubble g is not equal to g bubble f. That's not always the case. In some cases, it will be. You will see some cases in which this is going to be equal, but in this case, if you compare this result with that result, these two are not the same answer. All right, now let's do the composition of f with itself. To get the composition of f with itself, so we're going to write f evaluated at itself, f of x, which will be 2x squared, but instead of x, I'm going to write f of x itself, which is going to be, well, I'm going to use green just so you can see what I'm writing. Okay, so f of x is the function in green. All right, so, and if we expand the binomial here, I'm going to have the 2 outside first. That's going to be 4x to the 4th power minus 12x squared plus 9. That's the binomial squared. And then minus 3. The next is to distribute the 2 about every single term inside of the parentheses. So this will be 8x to the 4th power minus 24 x squared plus 2 times 9, which is 18, minus 3. All we do is to combine these two numbers to get 8x to the 4th minus 24 x squared plus 15. Alright, let's move on to the next page to find out what are we going to be asked to do. So now we are going to evaluate the function g at itself. Okay, let me see if I can put the page here so we can, yes, use that as a reference. Alright, so what we're going to do in this case is g evaluated at itself, g of x. So the function g, which is 4 times x, but I'm not going to write x anymore. I'm going to open parentheses and then plus 1, and then I'm going to evaluate it at itself for x plus 1. Which in this case, what we do is highlight what we're going to evaluate and then distribute the 4, that is 16x, plus 4 plus 1, which equals 16x plus 5. Okay. So now that we have these machines, these composite functions, if you want to think of this as machines, we are going to use them to find values. So what happens? Well, when we evaluate f at g of 1, what we're doing in this case is what is the value of inputting x equals 1 first at the machine g, which is the function g, and then whatever output we get, we input it in the function f. So in this case, we don't have to do each composition at a time because we already did that on the previous page. So let me use that as a reference. So in this case, we are going to evaluate this function, which is f composite g or f bubble g, and just evaluate that at 1. So 32 times 1 squared plus 16 times 1 minus 1. Well, we plug in 1, 1, 1, 1. And all we get here is, well, we get 32, because 1 squared is 1 times 32, that's 32. 1 times 16 is 16, and minus 1, final answer. Here I get 47. All right. Let's do G composite with F evaluated at 1. All right, so in that case, what do we do? So first, we go through F. The input 1 goes through F, and then whatever output goes as an input of G. All right, so let's see. I'm gonna show you the machine approach to this. First, we do these calculations, and then the machine imagery will come up next. Okay, so a G evaluated at f of 1. Okay, so all we do is use this function, which is 8x squared minus 11. Plug in 1. And that's 1 squared, which is 1 times 8 is 8, minus 11, that equals to negative 3. All right. Okay, let me show you the machine diagram for this, at least for the first two examples. All right, so let's see. Let me get a page here. I'm gonna go to another page. So we are gonna have the first machine in this case. So the input is gonna go like this. Input, which is 1, x equals 1. And in this case, we are going to evaluate first that at G goes through G first, G of x, which in this case for us is 4x plus 1, and evaluate. And evaluate it at 1. G of 1 equals 4 times 1 plus 1. That's going to output G of 1 equals 5. All right, that's what's going to give us. That's the output. Now, this output is going to be the input of a new machine. That new machine will be defined by the other function, which in this case is f of x equals, what was that? 2x squared minus 3. So f evaluated at 5 we get 2 times 5 squared minus 3. But what is 5 squared? 5 squared is 25. 25 times 2 is 50. But 50 minus 3 isn't that 47? Which is the same as what we obtained here. So you can do it step by step. I mean, that means using one machine first and then the other machine, or find the composition function, the composite function that as I did, and then just plug in the value for the one we want to know. Okay, so now let's see, let's f evaluated at itself, we already got from the previous page. Let me show it here. And we're going to evaluate this function, which is f composed with itself, at -1. Let's see what we get. So 8, -1 to the 4th power, minus 24 times -1 to the 2nd power, plus 15. So in this case, evaluated at -1, at -1. So -1 to the 4th power is +1 times 8, that's equal to 8. -1 squared, that's 1 times -24, that's -24. All right, and all we do is carry that that plus 15 here. So we get -1 over here. Final answer. Okay, and now let's do g evaluated at itself at -1, which we have here. The function g evaluated at itself corresponds to 16x plus 5. So 16x plus 5, and in this case, -1 is the value that we plug in. That's going to give us -16 plus 5 equals -11. Final answer for this. All right. Okay, now let's move on to the next example. For the next example, we are going to look at finding the domain of a composite function. However, in that case, we need to be very, very careful. How do we find the domain? All right, so for example, let's find, they're asking us to find f evaluated at g, or f composite with g, and f composite with itself. So for letter A, if you will, f evaluated at g, notice it has to be like an open circle so that it looks like a composition function, which is f evaluated at g of x. So in this case, my function f, which is 1 over x plus 2, I'm not going to write x plus 2, but I will rather plug in the function 4 over x minus 1. Let's highlight if you prefer. Okay, highlight the function. And that's what we are doing in here. All right. Now, in order to simplify this complex fraction right here, so I'm going to divide by 1 over here, and then I'm going to multiply numerator and denominator by the LCD, which is x minus 1, x minus 1. So I'm going to multiply x minus 1 times 1. That's going to give me x minus 1 divided by, I'm going to multiply x minus 1 times 4 divided by x minus 1. That will be 4 times x minus 1. And then divide that by x minus 1. And then finally, 2 times x minus 1. That's going to give me, in this case, we get this x minus 1 with x minus 1 cancel, and we are left with 4 plus 2x minus 2. All right. So in this case, let's simplify this to get x minus 1 divided by 2x minus, or plus 2 rather. All right, 2x plus 2. Okay, so this is f of g, f bubble g. All right, we need to find the domain of this function again because we have a rational expression or a rational function. We want to find all the values for which the denominator is 0. That is, okay, so this is final answer for the function that we were looking for. Let's find its domain. 2x plus 2, set it equal to 0. 2x cannot be negative 2, so x cannot be negative 1. All right, so this is what we'll look initially for the function. Okay, when we find the domain of this composite function. However, I claim this is not going to be the only one number excluded from the domain. So notice that when we plug in, when we substitute 4 over x minus 1, this 4 over x minus 1 already comes with a restriction. If you look at the denominator of this function, x cannot be positive 1. All right, so that's another number that has to be considered when it comes to looking at the domain. So using set notation, well, let's write down the usual number line, negative 1, 1. All numbers except these two are okay from the domain. Okay, so it's important to use interval notation. It's important to know both notations. However, most likely MyMathLab is going to ask you for maybe the two notations, but the one that asks the most is set notation, in which we say x such that x cannot be negative 1 separated by comma 1, and then use this curly brace to write down our set notation. So that's our first part of the problem. Let's do the second part, part B. Part B is to find the domain to find the composite function between f and itself, and then find its corresponding domain. So f bubble f of x will be f evaluated at itself. Okay. So our function f is 1 over x plus 2, but of course we are not going to write x plus 2. We are going to write the other function, which is f. Okay, so, and I'm going to highlight just so you can see where it is coming from. So that's 1 over x plus 2, all right? And that's what we put in the place of x. So in this case, again, this is going to give rise to a complex fraction. I'm going to multiply numerator and denominator by x plus 2, which is the LCD. So when I distribute, I get 1 times x plus 2. I get x plus 2 in the numerator. When I distribute the x plus 2 in the denominator, I will multiply x plus 2 times 1, which is simply x plus 2, and then divide by x plus 2. And then when I do the last part of the distribution, I multiply the 2 with the x plus 2. In this case, these guys cancel, but they don't cancel to 0. Need to be very careful with that. This cancels to 1 plus 2x plus 2. X plus 2 in the numerator. So then this is going to be 2x plus 3. That's going to be x plus 2 in the numerator and 2x plus 3 in the denominator. All right, so that's the composite function of f with itself. From here, however, okay, let me use a different color to highlight. I should have used orange here, just so we can distinguish from the green and the pink of the function that we highlighted earlier. So from here, I'm going to obtain that x cannot be negative 3/2. So one of the numbers that get excluded from the domain will be negative 3/2. However, that's not the only number, because notice how this function, when we do the composition, we're plugging in a function that already comes with restriction. So what is the restriction for this function? If you look at the denominator, x cannot be negative 2. All right? So in this case, x cannot be negative 2 and cannot be negative 3/2. So everywhere else, the function is okay, except at those values of x. Again, let's write this using interval notation, negative infinity to negative 2, union with negative 2 to negative 3/2, and union with negative 3/2 to positive infinity, using the other notation, set notation, x such that x cannot be negative 2 comma negative 3/2. Most likely on my MATLAB, again, you will be given this structure already. Here you will need to fill in these blanks, which is the numbers that are excluded from the domain. Alright, so from examples 1 and 2, we did composition of functions given two functions. Now, can we do the thing backwards? Of course. And the following is an example for which we're given a function that is already composite. Now they're asking us to split it apart and give us they're asking us for f and g such that the composition is x squared plus 1. And by the way, guys, for this type of exercises, there are more than one possible answer. For example, one possible answer is to have okay, so g is the one that goes inside. So g of x, I can think of it as being x squared plus 1, and f to be x to the 50th power. You know, because if we do f bubble with g, g is the one that goes inside, giving us x squared plus 1. Another possibility that I could think of is f equals, I don't know, maybe, well, let me actually put f of x, g of x, f of x. Let's make f equals x plus 1 to the 50th power, and g of x to be simply x squared. If we plug in x squared, we will plug it in where we see the letter x, which is here. That'll be x squared plus 1. So that's two possibilities, 1 and 2. Okay, there's again, for this type of exercises, the possibilities could be more than one. Let's look at another example. Big H of x equals 1 over x plus 1. So first of all, I can think of f of x and g of x. I could think of f of x as simply being 1 over x, and g of x, the function that goes inside, as x plus 1. Because if you plug in x plus 1 over here, that becomes 1 over x plus 1. Another possibility could be f of x being, for example, 1 over x squared plus 1. And well, we need to turn this x squared into simply x. We can do that by saying g of x equals the square root of x, because what happens if you input the square root of x inside of x squared? The radical cancels with the power, leaving us with just the x as what we have here. Again, two possibilities. There's a lot more possibilities that we could explore here. Why not? Let's do one more possibility that comes to my mind. F of x being 1 over x squared, and g of x equals the square root of x plus 1. What happens if you input x squared, the square root of x plus 1 with the x squared, the root with the power cancel, leaving us with the x plus 1 simply. So again, different possibilities. Okay, let's look at the next page, next and last page of this handout. So compositions, well, we can do this type of problems by tables of values or graphs. So let's look at one of those examples, and let me show you how to work on this type of problems. All right, so we have this table in which we're given values of x equals to -1, 0, 1, and 2, and some f and g, which we don't need to know the actual rule. We're just given the values. So we are going to calculate f composite g of 1. So first of all, what it would be great to do is change the notation. Okay, so first I need to evaluate g of 1. G of 1, so the output, when the output of g of the function g when the input is 1. So I'm going to go to x, which is the input. When the input is 1, what is the output in g? In g, the input 1 corresponds to a 0. And then this gets simplified, and now we look for the output of the function f when the input is 0. When the input is 0, f's output is 2. Now let's do the reverse order. G composite with f at -1. So first we need the output of f when the input is -1. So for f, when the input is -1, f is 1. And now we need to find the output of the function g when the input is 1. So we get 0. We already did it actually in the previous step. So 0 is final answer here. So let's do one more. F evaluated at g of 2. So first of all, we need the output of the function g when the input is 2. The input is 2. The output for g is 2 also. Now we need to find the input of the function, the output of the function f when the input is also 2, and we get -1. All right. Now let's look at the last example for this section to do the same with these two graphs. And given these two graphs, we are going to evaluate f composite g, which is f of g of 3. So we need to find f and g. Well, first of all, we need to define which one is f. So in this case, well, the functions are not labeled. The parabola will be f of x, and the line will be g of x. Okay, so looking at the line g of 3. What is g of 3? G, we get it from the line. So when x is equals to 3, y, or the output, is -3. Now we are going to find f of -3, but now because it's f, we're going to get it from the parabola. So if I go -1, -2, -3, what's the f? What's the output? +5. For letter B and last one of this handout, we get g evaluated at f of 2, which equals, okay, first of all, we evaluate f of 2. F gets evaluated from the graph, so when the input of f is equals to 2, the y value is 0. And then now we go to g of 0. We use the line when x equals 0, the output is -6. All right. And this is a good place to quit for this section. See you in the next video.